One server, 10 users. Everything works. Your web server, your application code, your database, all sitting on the same machine. Requests come in, the app handles them, the database responds. Response times are fast, CPU is barely moving, and if anything breaks, you SSH in, tail the logs, and fix it. Life is good. So why would you ever make it more complicated? Because before we talk about distributing anything, we need to be honest about what the simple setup actually gives you. Latency is trivial. Your app talks to the database in microseconds. It's basically a function call. Consistency is trivial. There's one copy of the data, no question about which version is correct. Debugging is trivial. One machine, one set of logs, one place to look. And deploys are trivial. Push new code to one server, restart, done. If your workload fits on one machine, seriously consider keeping it there. Distributed systems are a trade-off you accept when the alternative is worse, not a badge of honor. But single machines have hard limits, and sooner or later, every successful app runs into them. There are 4 of them. Let's walk through each one. First, CPU. Every server has a finite number of cores. When your application is doing real work, running business logic, serializing JSON, handling requests, you're burning cycles on those cores. As traffic grows, those cores fill up, and once they're saturated, new requests don't get processed. They queue, and that queue keeps growing. Response times climb. Users notice. You can't serve more traffic than your CPU can chew through. That's just physics. Second, memory. Your application and your database share a finite pool of RAM. As your dataset grows and as more concurrent requests hold state in memory, you fill that pool. And when you fill it, the operating system starts swapping to disk. This is where everything falls apart. A memory access that used to take nanoseconds now takes milliseconds. That's 100,000 times slower. Suddenly, every request is crawling, and you have no idea why, because on paper, the server is still running. Swap is where performance goes to die. Third and fourth, disk and network. Your database reads and writes through a single disk. Even with a fast SSD, there's a throughput ceiling. Thousands of transactions per second on one drive. Eventually, you hit it. And your server has one network interface. If you're serving large responses, streaming video, or holding thousands of open connections, you'll saturate that link too. Every pipe has a limit, and a single machine only has one of each pipe. And then there's the problem no amount of hardware can fix. A single server is a single point of failure. Hardware fault, kernel panic, a bad deploy, someone fills up the disk. Doesn't matter. When that machine goes down, your entire application goes with it. Every user, every request, gone. Now the first instinct, when things start getting tight, is usually to buy a bigger machine. More cores, more RAM, faster disks. This is called vertical scaling, or scaling up. And it works. For a while. The problem is the cost curve. Going from 8 cores to 16 cores might cost you twice as much. 16 to 32, 4 times as much. 32 to 64? You're now in specialized hardware territory. 10, 20 times the price of a commodity server. The cost is exponential, not linear. And no matter how much you spend, the biggest machine money can buy still has a ceiling. It's still one machine. It can still crash. So at some point, you hit the wall. And when you're there, there's only one direction left. Out. Instead of one giant machine, you split the work across several smaller ones. This is horizontal scaling, or scaling out. A typical first step, you put a load balancer in front of 2 or 3 application servers. Requests come in, the load balancer hands them out. Your database moves to its own dedicated machine, maybe with a replica standing by. Same 10,000 users. But now each server is sitting comfortably at 35 or 40%. There's headroom everywhere. And if you need to handle 20,000 users next month, you don't buy a bigger box. You just add another server. The load balancer picks it up. That's a completely different scaling model, but it is not free. Let's be fair about what you gained. Capacity. You're no longer bound by the specs of one machine. You're bound by how many machines you can deploy. Fault tolerance. One server dies, the others keep serving. Users might feel a hiccup. They don't go dark. Independent scaling. If the database is the bottleneck, you scale the database. You don't touch the app servers. Each piece grows at its own pace. And geographic distribution. Put servers in Tokyo, London, Virginia. close to wherever your users actually are. That's the difference between 20 milliseconds of latency and 200. These are real wins. But here's the part most people underestimate. Everything you just gained has a price, and the price is paid in problems that simply didn't exist before. Start with simplicity. When your app and your database were on the same machine, talking between them was cheap. If the database was embedded, like SQLite, Bolt, or Badger, it was a literal function call, nanoseconds. If it was Postgres or MySQL running locally, it was a Unix socket hop, microseconds. Either way, always successful, always in order. Now that call goes over a network, and a network call can do a lot of things a function call cannot. It can time out. It can arrive out of order. It can succeed on the other side while the response gets lost on the way back, so your client thinks it failed even though the work actually happened. Every single interaction between machines now has failure modes that simply weren't there before. Then, partial failures. In the old world, your system was either up or down. Simple. Now, server A is fine, server B is overloaded. The database is running a backup. Some requests succeed, some fail. Some are just slow. This is much harder to reason about, much harder to debug, because the system isn't broken. It's broken in patches. The network itself is unreliable. Packets drop, latency spikes, whole links go down. Your system has to survive all of it. And then, the big one, distributed state. If two servers both have a copy of your data, and a user updates their profile on server A, what does server B show the next request? The old version? The new version? A mix? This question sounds simple. It is actually one of the hardest problems in computer science. It has a name, consistency models, and we'll spend an entire lesson on it later in this course. Before we go further, here's a mental model you can carry through the entire course. Every design decision you make in a distributed system comes back to three properties. Scalability. Can the system handle more load? By adding resources, not by being rewritten, just by adding machines. Resiliency. When things go wrong, and they will go wrong, does the system contain the damage, or does one failure take everything down? And maintainability. Can real people actually understand it, debug it at 3 in the morning, deploy without fear? These three pillars are always in tension. More resilience usually means more complexity. More scale usually means new failure modes. Good design is finding the right balance for your system, not for Google's, not for Netflix's, yours. Alright, let's zoom out and look at the map you'll be navigating for the rest of this course. At the edge, clients, browsers, mobile apps, other services. Out in the wild, on unreliable networks. Their requests first hit a CDN. That's where your static assets live. JavaScript, CSS, images, served from edge locations close to the user. Dynamic requests flow through to a load balancer. The load balancer spreads traffic across your application services, maybe an auth service, an orders service, a payment service, each one independently deployed, each one independently scaled. Behind the services, your data layer, a primary database for writes, read replicas for fault tolerance and extra read capacity. A cache layer in front, serving hot data in microseconds instead of milliseconds. And a message queue, so services can talk to each other without being online at the exact same moment. Every single piece on this map gets its own lesson. The course is organized into 6 modules. Communication, how machines actually talk to each other. Coordination, the hard problems. Time, ordering, leader election, consensus. Coordination avoidance, systems that work without global coordination. Scalability, caching, partitioning, load balancing, storage, messaging. Resiliency, how things break, and the patterns that contain the damage. And operations, running all of it in production. 24 lessons, each piece in depth. Here's the thing, AI can generate code for any pattern in this course. What it can't do is tell you which pattern to use, or why one trade-off matters more than another for your specific system. That's systems thinking, and it compounds. Next up, TCP, how machines actually send data to each other reliably when the network can lose packets, reorder them, and duplicate them. That's where it all begins.